The cold does not return like an army. It returns first as a hesitation. Somewhere over the North Atlantic, winds that once carried a softer breath across the edge of the Ice Age begin to shift. Meltwater spreads from dying ice sheets into seas already crowded with floating ice. Forests that have been creeping northward through a warming world pause at their margins. Lakes hold the memory of longer winters. Insects vanish from places they had only recently reclaimed. The great animals of the late Pleistocene move through a landscape that is no longer quite the one their bodies expect, and above them, beyond sight, the machinery of the planet begins to stutter. Around 12,900 years ago, after thousands of years of warming, Earth suddenly turns back toward cold. It is not a full return to the deepest ice age, but it is close enough to feel like a reversal of fate. Temperatures drop sharply across much of the northern hemisphere. Glaciers stop retreating in some regions and advance again in others. Greenland records a fierce cooling. Europe feels forest retreat and open tundra spread. North America, still shaped by the enormous remains of the Laurentide ice sheet, becomes a continent of unstable water, ice, wind, and changing ground. For people living at the time, there is no name for this event. There's only weather that no longer behaves as expected. Seasons that seem to lengthen, familiar resources that shift away, and a world that had been opening suddenly becoming harsher again. Before we go deeper, take a moment to like the video and subscribe, if this is the kind of history and mystery you enjoy, because this is not simply a story about cold, it is a story about a planetary clue hidden in layers of ice, mud, bone, pollen, charcoal, metal, and silence. It is a story in which a real climate shock becomes tangled with one of the most debated ideas in modern prehistory, whether something from the sky, something from the earth, or something inside the climate system itself helped tip the world into the Younger Dryas. The Younger Dryas gets its name from a small Arctic alpine flower, Dryas octopetala, a Leuciassus hardy plant with pale petals that can live in cold, open ground. Its pollen appears in European sediments where warmer woodland pollen had been expected, as if the landscape itself had signed a document of retreat. The name is almost gentle, even delicate, but the event it marks is not gentle at all. The Younger Dryas is a cold reversal near the end of the last ice age. Beginning roughly 12,900 years ago, and lasting for more than 1,000 years before the climate rapidly warms again near 11,700 years ago. In human terms, that is longer than the rise and fall of many kingdoms. In geological terms, it is a sharp shiver. What makes the Younger Dryas so haunting is not only that the world became cold, but that it became cold quickly. The evidence remains incomplete in many places, and not every region responded in the same way, but the broad signal is unmistakable. The planet had been moving out of glacial conditions. Ice was shrinking, sea levels were rising, ecosystems were rearranging themselves into something closer to the Holocene world humans now know. Then, abruptly, the northern hemisphere seems to lurch backward. It is as though a door had opened toward a warmer age, only for a hand to seize it and drag it nearly shut. In Greenland ice, the change is written with an almost unnerving clarity. Snow falls year after year, compresses into ice, and traps tiny traces of atmosphere, dust, chemistry, and temperature signals. Layer by layer, the ice becomes a frozen archive of the sky. When scientists drill into it, they are not reading a story told in ink but in oxygen isotopes, trapped gases, acidity, volcanic residues, dust, and the invisible fingerprints of past air. From these records, The Younger Dryas appears not as a slow drift, but as a sudden climate reorganization. Cold arrives with a speed that forces a difficult question. What kind of system can change so fast after warming for so long? For a long time, the most widely discussed explanation has centered on meltwater and ocean circulation. As the Ice Age loosened its grip, huge volumes of fresh water poured from melting ice sheets. Fresh water is lighter than salty water. If enough of it enters the North Atlantic, it can interfere with the sinking of dense, cold, salty water that helps drive one of the great circulation systems moving heat through the ocean. If that circulation weakens, less heat reaches the high northern latitudes, and the climate around the North Atlantic can cool dramatically. This idea has physical logic behind it, and many climate scientists have treated freshwater-driven weakening of ocean circulation as a major candidate for the Younger Dryas trigger. Yet scholars still debate the exact route of the water, the timing, the volume, and whether fresh water alone can account for the full pattern. That uncertainty leaves space for other clues, and those clues have made the Younger Dryas far more famous than most climate reversals of the distant past. At some sites, researchers have reported unusual concentrations of platinum, microspherules, nanodiamonds, magnetic grains, melt-like materials, and dark sediment horizons. Some have interpreted these as possible traces of a cosmic airburst or impact by fragments of a comet or asteroid near the Younger Dryas boundary. The idea is powerful because it feels almost cinematic, a warming Ice Age world. A sudden flash from the sky, fires, dust, vanished animals, disrupted people, and a climate thrown into crisis. It is also deeply disputed. No confirmed crater of the right age and scale has settled the matter. Many proposed markers have been challenged. In recent years, the balance of evidence has grown more complicated, and some once publicized claims have not survived later scrutiny. A newer line of research has pushed the story in another direction, back down from the sky and into the restless interior of the Earth. Some strange geochemical signals in North American sediments may fit a volcanic source better than an extraterrestrial one. A platinum anomaly in Greenland ice, once seen by some as a possible cosmic clue, may also be explained by volcanic activity, perhaps from fissure-style eruptions in the North Atlantic region. Even more important, timing matters. A signal can be real and still not be the trigger. A chemical spike that arrives after the cooling begins cannot easily be the first domino, no matter how dramatic it looks in isolation. In this puzzle, the Earth keeps reminding investigators that a clue is not the same thing as a cause. So the mystery begins not with a crater, not with a comet, not even with a volcano, but with a change in the rhythm of Earth itself. A warming planet suddenly cools. Ice and ocean seem to renegotiate their balance. Strange chemical traces appear in archives separated by great distances. Some clues point upward, some point downward, and some point toward the ocean's deep engine. The Younger Dryas resists a single clean answer, because it may not have had a single clean cause. It may have been a cascade, a chain of pressures in a climate system already close to instability, where water, ice, atmosphere, volcanic forcing, and ecological feedbacks all helped shape the outcome. Before the cold reversal takes hold, the world is already in motion. The last ice age is not ending in a single clean thaw, as if winter simply loosens its hand and spring arrives everywhere at once. It is ending unevenly, with surges of warmth, pauses, local returns of cold, sudden floods, shifting forests, and coastlines that creep across drowned plains. The planet is coming out of a deep glacial state, but it is still carrying the weight of that older world. The great ice sheets remain enormous. Sea level is still far lower than today. Whole landscapes that now lie beneath shallow seas are open ground, crossed by rivers, animals, and people. The map of Earth is familiar in outline but strange in detail, with missing coastlines, exposed shelves, ice-walled horizons, and interior basins where meltwater gathers like an unstable memory of the glaciers. In North America, the Laurentide ice sheet still dominates the continent's northern heart. It is not merely a glacier in the ordinary sense. It is a frozen mass so large that it reshapes the crust beneath it, redirects rivers, stores impossible volumes of water, and creates its own weather at the edge of the sky. To its west, the Cordilleran ice sheet presses down from the mountains. Between and around these frozen worlds, lakes form and vanish as ice dams fail or reform. The land is full of temporary water, broad meltwater plains, braided rivers, cold lakes filled with silt, and channels that may carry catastrophic pulses when barriers break. What survives in the record suggests a continent not simply thawing, but reorganizing under pressure. South of the ice, the environment is mosaic rather than a single ice age scene. There are open grasslands, parklands, spruce forests, wetlands, marshy basins, sandy uplands, and river valleys rich with animals. The old stereotype of an endless frozen wasteland is too simple. In many places, late Ice Age North America is ecologically productive, though often harsh and unpredictable. Mammoths move through open country, using their huge teeth to grind tough grasses and sedges. Mastodons browse in wetter woodlands, their teeth better suited for twigs, leaves, and softer vegetation. Giant ground sloths, American horses, camels, bison, and ancient forms of deer and elk inhabit different corners of this shifting world. Saber-toothed cats and dire wolves still belong to the deeper story of the continent, though their worlds are beginning to narrow. The evidence remains incomplete, and local timelines differ, but the broad picture is one of abundance under stress. Across the Atlantic, Europe is also caught between ages. During the warm interval before the Younger Dryas, birch and pine expand into lands that had been more open and severe. Shrubs spread. Insects and small animals follow climate zones northward. Reindeer, horse, red deer, aurochs, and other animals occupy landscapes that change from generation to generation. The people of Western and Northern Europe live with that movement. They know river corridors, seasonal hunting grounds, stone sources, shelters, and open-air camps. Their tools, ornaments, and art belong to cultures that are not frozen in time. They adapt, trade, travel, remember, and experiment. In the sediments, a change in pollen can look like a quiet technical detail, but in lived experience it means different wood for fires, different animal paths, different shelter, different horizons. Farther east, across the vast spaces of Eurasia, the late Ice Age world is even more varied. Steppe tundra stretches in great belts, but it is not empty. It is a cold, dry, open biome capable of supporting grazing herds across distances that are difficult to imagine now. The Mammoth Steppe, as it is often called, is one of the great lost ecosystems of Earth. It covers immense regions during the Pleistocene, linking Europe, Siberia, Beringia, and parts of North America in ecological conversation. Grasses, herbs, mosses, and low shrubs create a landscape that can feed large animals in surprising numbers. One lesser-known detail is that this ecosystem is not simply a snowy version of modern tundra. It is drier, dustier, more open, and in many places richer in herbaceous plants than people expect. Its disappearance later is not just the loss of animals, but the loss of an entire environmental machine. Bringia, the land bridge between Siberia and Alaska, is among the most important of these vanished worlds. Today, much of it lies under the Bering and Chukchi seas, but before the full rise of post-glacial oceans, it is exposed land. It is not a narrow bridge in the simple cartoon sense, but a broad region of plains, rivers, uplands, and refugia. It may shelter plants, animals, and human groups during harsh climatic phases. Its western and eastern edges connect continents. But its interior is also a world of its own. Scholars still debate the precise timing and routes of human movement through and around this region, including coastal possibilities now hidden beneath the sea. That uncertainty is part of the difficulty some of the most important evidence may have drowned as the ocean rose. Human communities live through this unstable richness with skill that is easy to underestimate. They are not passive witnesses to climate. They make tools from stone, bone, antler, wood, hide, fibre, and plant materials. Though only some of these survive well enough for archaeologists to find, they follow seasonal rhythms, repair equipment, choose campsites, preserve knowledge, and read landscapes with close attention. In North America, Clovis technology appears near this broad window of time, known especially for finely made fluted projectile points. Though Clovis is neither the beginning of all people in the Americas, nor a simple single culture spread like paint across a map. Other traditions exist, and the story of early Americans is more complex than it once seemed. The archaeological record preserves only fragments, often stone tools and animal bones, while whole worlds of clothing, language, memory, music, and social life have disappeared. The coastlines of this world would be almost unrecognizable to modern eyes. Because so much water remains locked in ice, shorelines lie far beyond their present positions. River mouths extend across continental shelves. Islands are larger, straits narrower, and some now submerged lands are walkable country. Along these coasts, people may have moved, gathered shellfish, watched birds, fished, and followed marine resources, but many of their camps are now beneath the sea. This creates a strange bias in the story. The dry land archaeologists can reach today may not be where much of the action happened. A missing coastline can become a missing chapter of human history. So just before the Younger Dryas, the world is not peaceful, but it is opening. Ice is retreating. Forests are returning in some regions. Animals and people are adjusting to new opportunities. Water is rising. Rivers are changing. And old ecological borders are dissolving. Yet this opening world is fragile. Its warmth depends on circulation patterns, ice margins, ocean salinity, atmospheric currents, and feedbacks that can shift faster than any animal migration or human tradition can fully control. Beneath the apparent recovery, the climate system remains loaded with tension. The cold that comes next does not strike a stable planet. It enters a world already halfway transformed. The first clues do not look dramatic when they're lifted from the ground. They're not carved monuments, not written warnings, not a frozen scene preserved in perfect detail. They are darker bands in sediment, abrupt shifts in pollen, changes in tiny shells, layers of silt, fragments of charcoal, chemical irregularities, and bones lying in contexts that are rarely as clear as anyone would like. The Younger Dryas is not discovered as a single object. It emerges slowly from the patient comparison of many small records, each one incomplete, each one local, each one requiring scientists to ask whether a change in one place belongs to a larger planetary pattern. A layer in a lake bed, a change in an ancient bog, a pulse of dust in ice, a rearrangement of beetle species, a sudden return of cold-loving plants separately. These are details. Together, they begin to look like a world losing warmth with unsettling speed. In Europe, some of the earliest and most important signs come from sediments that preserve pollen. Pollen is almost weightless, easily overlooked, and yet it can travel through time with extraordinary power. Plants release it into the air, wind carries it across landscapes, and some of it settles into lakes, marshes, and peat bogs where low oxygen and steady burial can protect it for thousands of years. When researchers take cores from these deposits, they are not merely pulling mud from the ground. They are drawing out a vertical record of vanished vegetation. At one depth, the pollen may speak of birch, pine, and expanding woodland. At another, suddenly, cold-adapted plants return, including the Dryas flower that gives the event its name. The landscape seems to step backward. The warmth that allowed trees to spread weakens. Open ground expands. The record suggests not a gradual fading, but a reversal sharp enough to leave a recognizable ecological scar. This is one of the strange features of the Younger Dryas. It is both obvious and elusive. The broad cold reversal is well established, but the details vary sharply by region. Some places cool dramatically, others become drier, windier, or more seasonally unstable. Some records show abrupt changes, others show transitions that are blurred by local conditions, erosion, dating uncertainty, or the slow mixing of sediments. A lake does not record climate in the same way as an ice core. A cave does not preserve the same signal as a peat bog. A river valley can erase what a marsh protects. The evidence remains incomplete, not because the event was imaginary, but because Earth is a careless archivist. It saves fragments and destroys the rest. In lake sediments, the Younger Dryas can appear as a change in the chemistry and texture of deposited material. Colder conditions can shorten growing seasons, reduce biological productivity, alter runoff, and change the kinds of minerals carried into a basin. In some places, layers become richer in inorganic sediment as vegetation cover thins and wind or water moves more exposed soil. In others, changes in oxygen levels, aquatic organisms, or carbonate formation suggest new temperature and moisture regimes. These details rarely speak in simple sentences. They must be interpreted through models, comparisons, and careful dating. A dark layer may indicate organic accumulation, burning, wetland formation, erosion, or some combination of processes. A sudden shift may reflect climate, but it may also reflect a local flood, a changing shoreline, or a hiatus in deposition. This is why the Younger Dryas puzzle is not solved by finding a strange layer. The strange layer must be placed in time, compared with nearby records, and tested against alternative explanations. Bones add another kind of evidence, though they too can mislead if treated too simply. At some late Ice Age sites, the remains of mammoths, mastodons, horses, bison, or other animals appear near the time of the environmental change. Sometimes their bones lie with human-made tools. Sometimes they are found in natural traps, river deposits, sinkholes, caves, or ancient wetlands. They can show what animals were present, what they ate, how they moved, and sometimes whether humans interacted with them. But bones also move through time in complicated ways. Rivers can redeposit them, carnivores can scatter them, older remains can erode into younger sediments. Dates may come from the bone itself, from nearby charcoal, from surrounding sediment, or from associated materials, and each method carries uncertainty. What survives in the record suggests real ecological stress around the end of the Pleistocene, but no single bone bed can explain a continental transformation. The same is true for charcoal. Fire is one of the most tempting clues because it seems to promise drama. A rise in charcoal can suggest more burning, and more burning can suggest drought, vegetation change, human activity, lightning, or some extraordinary ignition event. In the popular imagination, the Younger Dryas boundary is sometimes pictured as a continent burning all at once beneath a cosmic blast. The scientific record is far less simple. Charcoal evidence varies from site to site. Some regions show increased fire activity, others do not. Fires were already part of many late Pleistocene ecosystems, and human groups could use fire locally without leaving a signal of catastrophe. A charcoal-rich layer may be important, but it must be treated carefully. Scholars still debate how much burning occurred, where it occurred, whether it was unusual, and whether it was cause, consequence, or coincidence. Then there are the famous dark layers often called black mats. They are especially known from parts of North America, where dark organic rich sediments appear near the end of the Pleistocene in some wetland or spring contexts. To some researchers, these layers seem to mark a boundary, a moment when environments changed, megafauna declined, and human traditions shifted. They became woven into the larger Younger Dryas story because they looked like a visible line between worlds. But black mats are not all the same thing. Some form in wet, marshy environments where organic material accumulates. Some may reflect changes in groundwater, plant growth, sedimentation, or local hydrology. They do not automatically mean continent-wide burning, cosmic fallout, or sudden destruction. Their importance lies partly in their timing and partly in the way they remind us that climate change can leave ordinary-looking marks that later become symbols of extraordinary events. One lesser-known difficulty is that the boundary itself is not always a clean line in the ground. The Younger Dryas onset is often given a date around 12,900 years ago, but translating that into a precise layer at a specific archaeological site is hard. Radiocarbon dates have error ranges. Different materials absorb carbon in different ways. Reservoir effects can make aquatic samples appear older than they are. Sediments can be disturbed by roots, burrowing animals, freeze-thaw action, erosion, or later human activity. Even when a layer contains an unusual chemical or mineral signal, scientists must ask whether it truly belongs to the onset or whether it arrived slightly before or after. Timing is not a technical footnote. In this mystery, timing is the difference between a trigger and an echo. This is why the first clues in the layers produce both excitement and caution. They reveal a real break in the late Ice Age world, a change sharp enough to be seen across many kinds of archives, yet they also warn against easy stories. A pollen shift can show cooling but not its cause. A black mat can mark environmental change but not necessarily disaster. A chemical spike can be real without being cosmic. A bone can show presence, absence, or stress, but not the whole fate of a species. The ground gives evidence in fragments, and every fragment must be handled with humility. The Younger Dryas begins to emerge from these layers as something more complex than a simple cold snap. It is a climate reversal written across landscapes, but written in a language that must be translated one clue at a time. The ground tells the story in fragments, but the ice tells it with a different kind of patience. In Greenland, snowfall gathers year after year, winter after winter, storm after storm, until each season is pressed beneath the next and slowly transformed into ice. At the surface, snow is light, full of air, and temporary. Deeper down, it becomes firn, then denser ice, and the empty spaces between snow grains close into tiny bubbles. Those bubbles become miniature samples of ancient atmosphere, sealed away long before any written history, long before cities, long before farming, long before the landscapes of the modern world had settled into their familiar shapes. The deeper the drill goes, the farther back the archive reaches, until the ice becomes a vertical memory of the sky. Ice cores matter because they are not only cold mud with a nicer appearance, they preserve multiple kinds of evidence at once. Their oxygen isotopes offer clues about temperature, their dust layers speak of wind, dryness, exposed ground, and atmospheric circulation. Their chemical impurities can record sea salt, volcanic sulfate, acidity, and distant eruptions. Their trapped gases reveal changes in the air itself. Some layers are annual or close to annual, allowing scientists to count time with a precision that many other archives cannot match. This does not make ice cores perfect. Layers can thin, flow, compress, or become harder to interpret with depth. Different cores require careful synchronization. Even in ice, the evidence remains incomplete in small but important ways, yet compared with many records from soil, rivers, caves, and lakes, Greenland ice is astonishingly direct. It is the closest thing Earth has to a climate diary written by snowfall. When researchers read the Younger Dryas in Greenland ice, they find a shift that feels almost too sharp for comfort. The warming before it, often associated with the Berling-Allerud interval, had brought milder conditions to the North Atlantic region after the long severity of glacial cold. Then the signal turns, isotopes change, dust increases, chemistry shifts. The record suggests that Greenland cools abruptly and remains cold through the Younger Dryas, before warming rapidly again around 11,700 years ago at the opening of the Holocene. The exact numbers depend on which method and which ice core are being discussed, but the pattern is not subtle. In the language of the ice, the Younger Dryas is a sudden interruption in the escape from the Ice Age. One of the most striking details is how quickly climate systems can reorganize. For people imagining climate as something that changes only over vast, almost motionless geological ages, the Younger Dryas is a correction. It shows that some parts of the Earth system can flip or lurch within decades, perhaps even faster in specific regions, when ocean circulation, sea ice, atmospheric winds, and feedbacks become aligned. This does not mean the whole planet changes everywhere in the same instant or in the same direction. The Younger Dryas is strongest in the North Atlantic world, with more complicated effects elsewhere. But the Greenland ice makes the central point difficult to ignore. The late Ice Age climate was capable of sudden movement. The planet was not a sleeping stone. It was a machine with thresholds. Within the ice, some clues are especially dramatic because they seem to arrive as spikes. A layer of volcanic sulfate, for example, may suggest an eruption whose aerosols reach the high atmosphere and spread over great distances. Dusty intervals can imply colder, drier, windier conditions or larger areas of exposed land. Sea salt chemistry can hint at sea ice and storm tracks. These signals do not act like simple labels. A sulfate spike does not automatically explain a cooling event. A dust increase does not name the cause of the wind. Each clue has to be placed in sequence, compared against other records, and tested against plausible mechanisms. Still, the ice allows a rare kind of detective work, not just asking what happened, but asking what happened first. This question of sequence becomes crucial when the story turns to the famous platinum anomaly near the boundary between the Berling-Alarud warmth and the Younger Dryas cold. Platinum is rare in Earth's crust and more abundant in some extraterrestrial materials, which is one reason it drew attention in discussions of a possible cosmic impact. In a simplified version of the story, a platinum spike in Greenland ice seemed like the kind of clue that might point upward, toward fragments of a comet or asteroid, but the newer and more careful reading is less friendly to that simple picture. The spike appears to last not as a single instant, but over a span of years. It also seems to occur after the onset of Younger Dryas cooling rather than before it. That matters enormously. A signal that arrives roughly decades late cannot easily be the spark that starts the fire, even if it still records something unusual. A volcanic explanation has become increasingly important here. Large volcanic eruptions, especially fissure-style eruptions capable of releasing unusual metals and aerosols, can leave chemical fingerprints in ice. Iceland and the North Atlantic volcanic region sit in a place where eruptions could affect both the atmosphere and the oceanic world, already central to the Younger Dryas puzzle. If a platinum anomaly once thought to be cosmic can be plausibly explained by volcanism, the mystery does not disappear, it changes shape. The question becomes not whether the clue is real, but what kind of Earth process produced it, and whether that process was cause, reinforcement, or coincidence. Scholars still debate details of timing and interpretation, but the old habit of treating every rare metal spike as a visitor from space has become much harder to defend. This is one of the quiet revolutions in the Younger Dryas story. The most dramatic clues are not always the most reliable guides. A rare element can seduce the imagination. A sudden spike can look like a signature, but ice cores force humility because they preserve order. They show whether a clue appears before cooling begins, during the cooling, after the cooling is underway, or near the later recovery. Timing turns spectacle into evidence, and sometimes evidence into a warning. The platinum signal may still be important, but it cannot be treated as a simple cosmic trigger without ignoring the calendar inside the ice. The ice cores also reveal that the Younger Dryas is not merely a single event, but part of a restless late glacial rhythm. Before it, the climate had already made abrupt moves. After it, the Holocene begins with startling speed. This broader pattern suggests that the climate system was already sensitive, especially around the North Atlantic, where ice sheets, meltwater, ocean circulation, sea ice, and atmospheric flow were tightly linked. The Younger Dryas may therefore be less like a bolt from nowhere and more like a threshold crossed by a system under pressure. A volcanic pulse, a freshwater rerouting, a change in sea ice, or some combination could push a vulnerable circulation pattern into a colder mode. No single explanation fully accounts for every record in every region. But the ice makes one thing clear: the world did not need millions of years to change. It needed the right pressure at the wrong moment. By the time the Greenland archive is read alongside lake beds, pollen records, marine sediments, cave deposits, and archaeological sites, the Younger Dryas becomes a layered mystery. The ground shows where landscapes changed. The bones show animals and people living through instability. The dark mats and chemical signals add controversy. But the ice gives the story its heartbeat. It marks the rhythm of cooling, persistence, and sudden warming. It reminds us that the sky itself can be preserved, that a snowfall can become testimony, and that a climate shock can hide for nearly 13,000 years in a column of frozen silence before a drill brings it back into human awareness. Among the many traces left by the Younger Dryas, Few have carried as much symbolic weight as the dark, organic-rich layers known as black mats. They are not found everywhere. They are not all the same age. They are not made by one single process. Yet in parts of North America, especially in spring-fed wetlands, marshes, pond margins, and low places where water and sediment gather, these dark bands appear close enough to the end of the Pleistocene to seem like a boundary drawn through the earth. Above them and below them, the world can look different. Animal bones, plant remains, stone tools, and sediment textures sometimes shift across that line. To anyone searching for a moment when the Ice Age world changed, the black mat can feel almost too tempting, as if the ground itself has darkened at the instant history turns. But the first rule of the black mat is that it must not be mistaken for a single event. The name sounds simple, almost dramatic, but it describes a family of deposits rather than one universal layer. Some black mats form when wetlands expand and organic material accumulates in waterlogged conditions. Some reflect changes in groundwater, the growth of algae or marsh plants, fine-grained sediment settling in quiet water, or a shift from drier surfaces to saturated environments in certain places. The darkness can come from carbon-rich plant remains. In others, it may include charcoal, minerals, or decomposed organic matter. A black mat can mark environmental change without marking catastrophe. It can be a sign of wetness, not fire, of local hydrology, not global disaster. The evidence remains incomplete because each black mat must be understood in its own landscape before it can be used in a continental story. This has not stopped the layers from becoming central to the Younger Dryas debate. When researchers and storytellers first began tying black mats to the Younger Dryas boundary, the appeal was obvious. A dark layer appears near the time when climate cools, when many large animals are disappearing, and when archaeological traditions in North America are changing. The layer seems to separate one world from another. Below it lies the late Pleistocene, with mammoths, mastodons, horses, camels, giant ground sloths, and other animals still part of the living continent. Above it lies a different world, increasingly Holocene in character, with many of those animals gone. In a narrative sense, the black mat becomes a curtain falling. In scientific terms, it is much more difficult. At some sites, black mats are associated with remains of megafauna, including animals that disappear from North America near the end of the Pleistocene. That association helped give the deposits a sense of drama. But association is not causation, and proximity in sediment is not always proximity in lived time. A bone may be older than the layer that covers it. A surface may remain exposed for years before burial. A spring may attract animals for generations, leaving remains from multiple moments in one place. Sediment can accumulate slowly, then quickly, then stop. Burrowing, root action, erosion, trampling, and water movement can disturb the order that later investigators wish were clean. What survives in the record suggests that black mats often form in places where water, animals, and people all had reason to gather, which makes them rich archives but also complicated ones. The popular version of the black mat story sometimes imagines a vast burn layer spread across North America, a blanket of soot from continent-wide fires ignited by a cosmic airburst. That image is powerful, but it does not match the cautious reading of the evidence. Some black mats contain charcoal or burned material. Some sites show increased fire indicators near the Younger Dryas boundary. But many black mats are not primarily soot. They are not a single ash sheet. They do not form one continuous continent-wide layer laid down in one terrible day. Fire is part of the late Ice Age story, as it is part of nearly every terrestrial ecosystem. But the black mats themselves cannot be reduced to a simple fire scar. Scholars still debate how widespread burning was, how unusual it was, and how it relates to climate, vegetation change, human activity, and local conditions. The hydrological meaning of many black mats may actually be one of their most important lessons. At the end of the Pleistocene, as climate shifts and groundwater systems respond, some landscapes become wetter in low areas, even as the broader climate becomes colder or drier in seasonal terms. Springs flow differently, water tables rise or fluctuate, wetlands expand in places where organic material can accumulate and be preserved. A black mat may therefore record a landscape reorganizing under stress, not merely a disaster layer. It may show that the Younger Dryas changed how water moved through the ground, where plants grew, where animals came to drink, and where sediments settled. This kind of change is quieter than a firestorm, but it is no less meaningful. For animals and humans living on the land, the placement of water is the placement of life. There is another lesser-known complication. The same kind of dark, organic layer can form at different times for different reasons. Wetlands do not wait for global climate events to create black sediment. They form wherever local conditions allow organic matter to build up. This means that a black mat must be dated carefully before it can be tied to the Younger Dryas. Even then, dating can be difficult. Radiocarbon samples may come from plant fragments, charcoal, bone collagen, or surrounding organic material, each with its own problems. Old carbon can enter a system through groundwater. Younger roots can intrude downward. Charcoal can be redeposited from older fires. If a sample is taken from just above or below the layer, the date may not capture the exact moment the layer began. The boundary that looks sharp to the eye may be blurred in time. Because of these challenges, the black mat has become a kind of test for how the Younger Dryas should be studied. One approach seeks a single dramatic boundary, a line where climate, extinction, human culture, and cosmic or volcanic clues all converge. Another approach sees the black mats as local expressions of a wider environmental transition, valuable but not uniform, suggestive but not decisive. The second view is less cinematic, but often more consistent with how landscapes behave. A continent does not change like a page turning. It changes through watersheds, soils, vegetation zones, animal ranges, fire regimes, and human decisions, all moving at different speeds. The black mat may be one visible trace of that uneven transformation. Still, it would be a mistake to dismiss these layers as unimportant simply because they are not a universal disaster mark. Their importance lies in the fact that they appear at places where the end-Pleistocene world can be read with unusual richness. They preserve pollen, plant remains, microscopic organisms, charcoal, bones, chemical signals, and sometimes archaeological materials near a time of major change. They show that wetlands, springs, and lowland basins became sensitive recorders of a shifting climate. They also show why a mystery can deepen as evidence improves. The more carefully the black mats are studied, the less they support a simple story, but the more they reveal the complexity of the world that was changing. In this sense, the black mat is less like the ash of an explosion and more like a shadow cast by many forces at once. It belongs to water, plants, sediment, animals, climate, and time. It marks places where the land became wet enough, still enough, and organic enough to preserve a dark memory of transition. It may sit near the disappearance of great animals, near changes in human tools, near unusual chemical signals, and near the onset of a cold reversal. but it does not explain all of them by itself. It is a clue, not a verdict. And in the Younger Dryas puzzle, that distinction matters more than almost anything. The idea that something came from the sky did not appear because the Younger Dryas was imaginary. It appeared because the event was real, abrupt, and difficult to explain with perfect confidence. A climate system already unstable near the end of the Ice Age suddenly lurched into cold. Many large animals vanished from North America within a broad window of time close to this transition. Clovis technology, once treated too simply as the signature of the first Americans, seemed to change or fade in ways that invited dramatic explanation. Dark layers appeared at some sites. Unusual microscopic materials were reported. Rare elements were measured. The pieces did not form a calm picture. They formed a puzzle with enough gaps for a powerful hypothesis to enter. The Younger Dryas impact hypothesis, often shortened to YDIH, proposes that fragments of a comet or asteroid struck Earth or exploded in the atmosphere near the onset of the Younger Dryas, roughly 12,900 years ago. In its strongest versions, this event ignited widespread fires, injected dust and aerosols into the atmosphere, disrupted climate, contributed to the extinction of late Pleistocene megafauna, and helped destabilize human cultures in North America. It is easy to understand why the idea captured public imagination. It joins several great mysteries into one dramatic moment: sudden cold, vanished animals, changing archaeology, dark sediment, and traces that seem to glitter with cosmic possibility. A single event from the sky appears to tie the knots together. But a beautiful knot is not necessarily a correct one. From the beginning, the impact hypothesis has lived in tension between intrigue and resistance. Its supporters have argued that multiple sites contain a boundary layer with unusual materials, magnetic microspherules, carbon spherules, nanodiamonds, melt-like glass, iridium or platinum anomalies, and other possible high-temperature or extraterrestrial indicators. Some of these materials, they argue, are difficult to explain through ordinary terrestrial processes alone. They see the distribution across distant sites as evidence for a large, unusual event, possibly not a single crater-forming impact, but an airburst or swarm of fragments exploding above ice, water, or land. If the object broke apart over a broad region, the absence of one neat crater might not be surprising. That last point is one reason the hypothesis has survived in popular discussion. People often imagine impacts as crater-making events like Meteor Crater in Arizona, a visible wound in the landscape, but airburst can explode above the ground, as seen in the Tunguska event of 1908, which flattened forest without creating a classic crater. Smaller airbursts happen more often than most people realize. Larger ones are rarer but physically possible. A comet made of fragile material could break apart in the atmosphere. A strike on an ice sheet might leave little lasting crater once the ice melts. These possibilities keep the door open in theory, and they give the Younger Dryas impact idea a way to answer one of the most obvious objections. Yet the problem is not only the missing crater. The deeper problem is reproducibility, timing, identification, and context. When unusual particles are reported at a boundary, other scientists must be able to find them, identify them in the same way, date them precisely, and show that they are not produced by more ordinary processes. Magnetic microspherules can form in cosmic events, but they can also come from volcanism, lightning, wildfires, industrial contamination in younger contexts, or other high-temperature processes. Melt-like glass can be created by impacts, but also by volcanism, fire, lightning, or human activity in some settings. Nanodiamonds are fascinating, but their identification is technically difficult, and different forms can have different origins. Platinum may hint at extraterrestrial input, but it can also have volcanic explanations. A clue that seems cosmic in isolation may become terrestrial when placed in a fuller geochemical setting. This is where the story becomes less like a disaster movie and more like a courtroom where every witness is cross-examined. A particle is not allowed to be merely strange. It must be strange in the right way, at the right time, in the right layer, with the right chemistry, found by methods that others can test. A spike in one core must line up with other records. A date must be tight enough to matter. A claimed boundary must not be a mixed deposit, an eroded surface, or a layer formed centuries away from the event it is supposed to mark. The evidence remains incomplete, and because the stakes are high, the scrutiny is high as well. The impact hypothesis gained major attention in the early 21st century when researchers proposed that a cosmic event at the Younger Dryas boundary could explain several late Ice Age changes at once. For many outside the field, the idea had an almost mythic quality. It suggested that prehistory had been interrupted by a sudden celestial violence, a forgotten catastrophe preserved only in microscopic debris. It also arrived at a time when public fascination with abrupt climate change, ancient disasters, and lost worlds was growing. The Younger Dryas became more than a climatic episode. It became a symbol of how quickly the familiar can disappear. But mainstream caution has remained strong. Many climate scientists already had a plausible mechanism involving meltwater and Atlantic circulation. Many archaeologists were skeptical of linking Clovis changes to a single catastrophe. Paleontologists studying extinction saw long, complex patterns involving climate change, habitat transformation, human hunting, reproductive rates, ecological stress, and regional timing differences rather than a clean kill horizon. Geologists and geochemists questioned whether some proposed impact markers were correctly identified or consistently present. No single explanation fully accounts for the late Pleistocene transformation, but that does not mean every dramatic explanation becomes equally likely. One lesser-known but important point is that the Younger Dryas did not affect the entire planet in the same simple way, and the extinctions were not perfectly synchronized everywhere. Some megafauna disappeared before the onset, some near it, some after it, and some survived in refuges for surprisingly long periods. Mammoths, for example, persisted on islands long after mainland populations vanished. This unevenness does not rule out a sudden event influencing the system, but it weakens any version of the story that depends on one instantaneous global catastrophe doing all the work. The Earth rarely tidies its endings for human convenience. The most careful way to tell the cosmic hypothesis is therefore not as a proven answer, but as a controversial proposal born from real anomalies and sharpened by real scientific disagreement. It asks whether some extraordinary atmospheric or extraterrestrial event may have added stress to a world already near a climatic threshold. That is a narrower and more cautious claim than saying a comet caused the Younger Dryas, burned a continent, ended Clovis, and wiped out the megafauna. The broader claim has not been accepted by most specialists. The narrower question remains part of the debate. Though recent evidence has made volcanic and ocean circulation explanations more compelling for several of the most famous clues, still, the cosmic idea matters because it changed how the Younger Dryas was discussed. It forced researchers to examine boundary layers more closely, to test particles more carefully, to refine dating, to compare sites, and to ask what counts as extraordinary evidence. Even where the hypothesis has weakened, the investigation has produced sharper questions. Were the strange materials truly synchronous? Are they impact markers, volcanic residues, local fire products, or mixed signals? Did any external forcing help tip the climate system, or was the engine already turning toward cold through ice and ocean dynamics alone? The sky may not hold the answer, but the search for a skyborne cause has made the ground speak in greater detail. The Younger Dryas impact hypothesis survives, then, not as a settled truth, but as a disputed doorway into the larger mystery. It reminds us that science is not only a collection of facts, but a process of testing stories against stubborn evidence. Some stories become stronger, some become narrower, some lose pieces, some are abandoned. At the edge of the Younger Dryas, the cosmic story still glows faintly because the event itself remains dramatic. But the glow is not proof. It is an invitation to look more closely at the particles, the dates, the ice, the oceans, and the Earth's own violent powers before deciding whether the cold came from above, below, or from the fragile circulation of the planet itself. Once the cosmic idea enters the story, the Younger Dryas becomes a mystery of the very small. The grand images are easy to imagine: a bright object crossing the sky, ice sheets trembling beneath atmospheric blasts, forests burning, animals fleeing across cold plains. But the actual argument depends on things nearly invisible to the unaided eye. It depends on grains smaller than sand, particles trapped in sediment, glassy droplets, rare metals measured in tiny concentrations, and crystals whose structure can only be studied through specialized instruments. The debate moves from landscapes into laboratories. A continent-wide catastrophe, if it happened, must prove itself in specks of matter. Magnetic microspherules are among the most frequently discussed clues. Under a microscope, they can look like tiny rounded beads, often rich in iron or other metals, formed when material melts and then cools quickly into spherical shapes. Their roundness is part of their appeal. A droplet of molten material, suspended briefly in air, naturally pulls itself into a sphere before hardening. Such particles can form during impacts, where extreme heat and shock melt rock or metal and scatter droplets across the landscape. They can also form during volcanic eruptions, lightning strikes, intense fires, and other high-temperature processes. That is the difficulty. The shape alone does not reveal the story. A microspherule is not automatically a cosmic fingerprint. It is a question in the form of a bead. To make the case for an impact, researchers must show more than the presence of microspherules. They must show that the particles occur at the right boundary, that they appear across widely separated sites at the same time, that their chemistry matches an impact or extraterrestrial source better than terrestrial alternatives, and that contamination or reworking can be ruled out. This is harder than it sounds. Sediments are not sealed museum drawers. Wind can move fine particles. Water can concentrate heavy grains. Ancient surfaces can erode and redeposit material. Burrowing animals and roots can disturb layers. A particle found near the Younger Dryas boundary may have formed earlier, arrived later, or been moved from another context. The evidence remains incomplete because each site has its own history before it becomes a data point in a global argument. Nanodiamonds are even more intriguing and even more difficult. Diamonds can form under extreme pressure and temperature, which is why their reported presence in Younger Dryas boundary layers drew attention. Some supporters of the impact hypothesis argued that certain forms of nanodiamond might indicate a high-energy cosmic event. The idea is captivating tiny diamonds scattered across the edge of the Ice Age, glittering proof of a blast too old for memory. But identifying nanodiamonds is technically demanding. Different carbon structures can be confused, Some forms may arise through processes unrelated to impacts. Samples require careful preparation and interpretation, and not all researchers have been able to reproduce the same findings in the same way. In science, a beautiful particle is not enough. It must remain beautiful after other laboratories examine it. Melt glass and glass-like materials add another layer of complexity. When rock, soil, or sediment is heated intensely and cooled quickly, it can become glassy. Impacts can certainly produce such materials. But volcanism can also produce glass, so can lightning, especially when it fuses sandy soil into fulgurites. Very hot wildfires may alter minerals, and human activity can produce glassy residues in some contexts, though that is less relevant for many late Pleistocene sites than in younger archaeological layers. The important point is that high temperature alone does not name the source of heat. A glassy fragment must be studied for its mineralogy, chemistry, formation conditions, and geological setting. Scholars still debate whether some Younger Dryas glass-like materials require extraordinary temperatures best explained by impact, or whether terrestrial processes can explain them more cautiously. Then there are the rare metal anomalies, especially platinum. Platinum has become one of the most famous and misunderstood clues in the Younger Dryas debate. Because platinum group elements are more common in some meteorites than in ordinary crustal rocks. A platinum spike can feel like a message from beyond Earth, but rare does not mean alien. The Earth itself has deep reservoirs of platinum group elements, and volcanism can bring unusual geochemical signatures into sediments or ice. Large eruptions can inject aerosols and fine particles into the atmosphere, spreading chemical traces over broad areas. In recent interpretations, some platinum anomalies once treated as possible cosmic hints look increasingly compatible with volcanic sources. One particularly important Greenland signal appears not to fall exactly at the beginning of Younger Dryas cooling, but after it is already underway. That turns a supposed trigger into something more likely to be a later episode, a related disturbance or a separate clue altogether. This matter of timing is unforgiving. Imagine a detective finding a match beside the ashes of a house, only to learn that the match was dropped years after the fire. The match may still matter, but it cannot be the cause. The same logic applies to the Younger Dryas. A chemical spike, a particle layer, or a dark horizon must line up with the event it is supposed to explain. If it appears too late, too early, or across a wide smear of time, its role changes. It may mark environmental stress. It may serve as a useful stratigraphic marker. It may record volcanic activity, atmospheric dust, local burning, or sediment focusing. But it cannot simply be promoted into the first domino. The debate has sharpened further because some claims once presented as strong evidence have later faced serious criticism or withdrawal. In recent years, high-profile papers connected to cometary dust, microspherules, platinum anomalies, and shocked quartz have been challenged over issues such as dating, sampling strategy, identification of materials, and interpretation of data. In some cases, materials proposed as unusual impact-related particles were reinterpreted by specialists as ordinary biological or geological remains. This does not mean every unusual Younger Dryas signal is meaningless. It means the standard of proof has risen, as it should. Extraordinary explanations must survive ordinary checking. Shocked quartz is a useful example because it has a strong reputation in impact science. Under extreme shock pressures, quartz can develop microscopic deformation features that differ from ordinary cracking or tectonic strain. In confirmed impact structures, shocked quartz can be a powerful clue, but identifying it correctly requires expertise, and not every fractured quartz grain is shocked by impact. geological stress, transport, weathering, and sample preparation can produce features that look suggestive but are not diagnostic. If the age model of a sediment layer is uncertain, or if similar quartz features appear outside the supposed boundary, the argument weakens. The power of shocked quartz depends precisely on its specificity. Remove that specificity, and the clue loses force. This is where the Younger Dryas dispute becomes a lesson in how science handles mystery. The public often sees debate as weakness, as if uncertainty means nobody knows anything. But here, uncertainty is the method doing its work. A claimed cosmic particle must be tested against volcanic explanations. A rare element must be checked against timing. A dark layer must be separated from wetland formation. A global claim must survive local geology. No single explanation fully accounts for every strange signal, but newer work increasingly suggests that some of the most famous cosmic clues may belong to Earth's own processes: volcanism, hydrology, fire, sediment concentration, and the complicated behavior of a climate system under stress. The microscopic clues still matter because they keep the Younger Dryas from becoming too simple. They show that something unusual was happening in the atmosphere, sediments, and ecosystems around this transition, but they do not all point in one direction. Some point upward only at first glance. Some point downward into volcanoes and deep earth chemistry. Some point sideways into wetlands, rivers, winds, and local disturbance. The mystery is not that there are no clues. The mystery is that there are too many kinds of clues, and they do not all agree. At the boundary of the Younger Dryas, the smallest particles carry the largest burden to decide whether the story belongs to the sky, the ice, the ocean, the volcano, or some restless combination of them all. Beneath the argument over particles and rare metals lies a larger fact that needs no comet to make it dramatic. North America at the end of the Ice Age is a continent under strain. Its northern half is still burdened by ice so heavy that the crust beneath it has been pressed downward. Its rivers are searching for new paths. Its lakes are trapped behind unstable dams of ice and sediment. Its coastlines are not where they are today. Its winds carry dust from exposed ground. Its animals move through habitats that are shifting faster than many long-lived species can comfortably follow. The whole continent is not waiting calmly for one great event to change it. It is already changing, and every piece of that change can amplify the next. The Laurentide ice sheet is the central presence in this story. At its maximum, it covered millions of square kilometers, burying much of Canada and parts of the northern United States beneath ice that could be more than a kilometer thick. By the time of the Younger Dryas onset, it has retreated from its greatest extent. But retreat does not mean weakness in any simple sense. A shrinking ice sheet can be extremely dangerous to the climate system because it releases water, exposes new land, creates unstable margins, and alters the reflectivity of the surface. It can feed enormous lakes along its edge. It can block old drainage routes and open new ones. It can collapse in pulses rather than melt politely. The ice is dying, but in dying it becomes powerful. At the southern and western margins of the ice, meltwater collects in basins whose names are now used for ancient giants, Lake Agassiz, Lake Ojibwe, and other proglacial lakes that once spread across parts of central North America. These are not ordinary lakes in the modern recreational sense. Some are inland seas, broad and cold, held in place by ice dams and shifting outlets. Their shorelines leave traces on hillsides. Their sediments settle in quiet basins. Their waters rise and fall as ice blocks one path and opens another. A small change in an ice margin can reroute vast volumes of fresh water from one drainage system to another. The continent is full of plumbing under construction, and some of the pipes are made of ice. Lake Agassiz is especially important because it may have held enough fresh water to matter beyond North America. Fed by glacial melt, it grew and shrank through multiple phases, sometimes draining south toward the Mississippi system, sometimes east, perhaps north or northwest, depending on the configuration of ice and land. Scholars still debate the exact routes and timing of its major outflows near the Younger Dryas. And that debate matters because meltwater must reach the right ocean at the right time to influence climate strongly. It is not enough for water to exist. It has to go somewhere consequential. If large amounts of fresh water enter the North Atlantic or Arctic connected systems, they can alter salinity and density in regions tied to ocean circulation. But the sedimentary evidence for precise routes can be fragmentary, buried, eroded, or drowned. The water left marks, but not always a clean map. This is one of the quieter frustrations of the Younger Dryas puzzle. The most important event may have been a rerouting rather than a single spectacular flood. A catastrophic outburst flood leaves dramatic scars, giant ripples, scoured channels, boulder bars, torn landscapes. A more distributed or repeated discharge can be harder to identify, especially after thousands of years of erosion, vegetation growth, later flooding, and human alteration. The landscape may preserve enough to suggest instability, but not enough to settle every argument. The evidence remains incomplete, and the incompleteness is not a failure of effort. It is the consequence of asking water, ice, mud, and time to preserve a detailed confession. The ice sheet also affects the atmosphere. A mass of ice that enormous is not passive terrain. It chills the air above it, redirects winds, influences storm tracks, and helps maintain strong temperature contrasts across the continent. As the ice retreats, those atmospheric patterns change. Dry exposed sediments along glacial margins can become sources of dust. Vegetation trying to colonize newly uncovered ground may be sparse at first, leaving surfaces vulnerable to wind erosion. In Greenland ice and other records, changes in dust can reflect a world where wind patterns, aridity, and exposed landscapes are all shifting. Dust is not only dirt in the air, it is evidence of surfaces without stable cover, of winds strong enough to carry the ground away grain by grain. South of the ice, ecosystems are being stretched. As climate warms before the Younger Dryas, plants and animals track changing conditions northward and upward where possible. Forests expand into some areas. Open habitats contract or reorganize. Wetlands form in new places. River valleys change their vegetation. But these movements are uneven because soils, precipitation, fire, topography, and animal behavior all matter. Then, when the cold reversal begins, some of these ecological advances are interrupted. A plant community that took centuries to establish may be pushed back. Animals that had followed the improving climate may find themselves caught between older ranges and new stress. For large mammals with slow reproduction and large territory needs, repeated environmental instability can be costly, even without a sudden catastrophe. The continent's water systems may also create local refuges and local traps. Springs and wetlands can become especially important during stressful transitions, drawing animals and people to reliable water sources. This is one reason sites near ancient springs and wet basins can preserve rich records of late Pleistocene life. But the same places can produce misleading concentrations. If many animals visit the same water source across centuries, their remains may appear clustered in a way that feels like a sudden event. If people also visit the place, leaving tools or butchered remains, the archaeological picture becomes more complicated still. What looks like one moment may be many moments stacked together by water. Another surprising detail is that deglaciation changes the land itself. When an ice sheet melts, the crust beneath it begins to rebound, rising slowly after being relieved of immense weight. This process, called isostatic rebound, can alter drainage routes, tilt lake basins, shift shorelines, and change where water flows. The land does not simply sit there while ice melts on top of it. It responds. In some regions, rebound may have helped redirect meltwater by lifting old outlets or opening new gradients. This means the Younger Dryas landscape is dynamic in 3 dimensions. Ice retreats, water moves, and the ground rises. A map drawn for one century may be wrong for the next. Against this background, the search for a single trigger begins to look different. A continent already full of melting ice, unstable lakes, exposed sediments, changing ecosystems, rebounding crust, and shifting winds does not require much additional pressure to cross a threshold. A volcanic episode could cool the atmosphere temporarily and alter precipitation. A rerouted meltwater pulse could freshen key ocean regions. Expanding sea ice could reflect sunlight and reinforce cold. Changes in vegetation and dust could deepen regional effects. None of these mechanisms must work alone. In a stress system, the most important cause may be the combination, not the most dramatic individual part. North America at the edge of the Younger Dryas is therefore not merely the stage on which the mystery happens. It is one of the engines of the mystery. Its ice holds the water, its lakes store the instability, its winds carry the dust, its changing habitats shape the fate of animals and people, its sediments preserve dark layers, strange particles, and broken pieces of the older world. The continent is not silent beneath the cold. It is creaking, draining, rebounding, thawing, freezing again, and sending signals outward into the ocean and atmosphere. Long before any final explanation can be chosen, the land itself shows why the Younger Dryas could happen quickly. The system was already near the edge. The stress stored in North America does not remain on land. Water always searches for a way out, and at the end of the Ice Age, the way out matters more than almost anything. A lake trapped against an ice margin is not only a local feature. A meltwater route is not only a river. When enough fresh water leaves the continent and enters the northern seas, it can touch one of the great engines of global climate, the circulation of the Atlantic Ocean. The Younger Dryas mystery therefore widens from glaciers and sediments into something deeper and more difficult to imagine, a moving architecture of salt, cold, density, wind, and sinking water. The ocean is not a blue surface lying beneath the weather. It is part of the weather's memory, and sometimes part of its trigger. In the modern Atlantic, warm salty water flows northward near the surface, carrying heat from lower latitudes toward Europe and the North Atlantic world. As this water cools in high northern regions, it becomes denser, because it is salty, and because cold water is heavier than warm water. It can sink into the deep ocean and help drive a larger overturning circulation. This system is often discussed through the term AMOC, the Atlantic Meridional Overturning Circulation. It is not a single river in the sea, and it should not be imagined as a neat conveyor belt with rigid edges, but the conveyor image is useful enough to show the basic idea: heat moves north near the surface. Dense water sinks, and deeper waters return southward over long time scales. Change the density of northern surface waters, and the whole pattern can weaken or reorganize. Fresh water is the problem because it dilutes salt. Pour enough fresh meltwater into the northern Atlantic or connected Arctic routes, and the surface becomes less salty, less dense, and less willing to sink. If sinking slows, less warm water may be pulled north. Sea ice can expand. The atmosphere responds. Winds shift. Snow and ice reflect more sunlight. A regional cooling can become reinforced by feedbacks that keep the cold in place long after the first pulse of water has passed. This is one of the strongest mainstream explanations for the Younger Dryas. The climate system did not need an impact to turn cold. It may have needed a flood of fresh water into a vulnerable ocean. Yet the difficulty has always been the route. It is one thing to say glacial meltwater could weaken the Atlantic circulation. It is another thing to prove exactly where the water went at exactly the right time. Lake Agassiz and related meltwater systems could drain south into the Mississippi, east toward the Great Lakes and St. Lawrence, north into Arctic-connected channels, or through pathways that changed as ice margins opened and closed. Some proposed routes deliver fresh water more directly to regions where deep water formation matters. Others may have weaker or delayed effects. Scholars still debate which route dominated near the Younger Dryas onset, and whether the volume, timing, and destination of meltwater were sufficient by themselves. The evidence remains incomplete because ancient drainage routes can be erased, buried beneath later sediments, drowned by rising seas, or confused by multiple outflow events. There is also the possibility that the freshwater story is not one single flood but a sequence of reorganizations. A dramatic outburst is easier to imagine and easier to narrate. But climate systems may respond to repeated pulses, rerouted drainage, and gradual freshening that crosses a threshold. The ocean does not care whether the water arrives with cinematic violence or quiet persistence. It responds to density, stratification, sea ice, wind, and heat exchange. A meltwater event may begin modestly and become powerful only when the circulation is already weakened by other forces. A volcanic cooling pulse, for example, could encourage sea ice expansion or alter atmospheric patterns, making the North Atlantic more sensitive to freshening. In that kind of scenario, the Younger Dryas is not caused by one clean blow. It is caused by several pressures arriving in a dangerous order. One lesser-known detail is that sea ice itself can help lock the system into cold. When sea ice expands, it reflects sunlight and insulates the ocean from the atmosphere. In some places, sea ice formation rejects salt into the surrounding water, affecting density in complicated ways, while fresh water and melting sea ice can also stabilize the surface. The pattern depends on region and season, but in broad terms, expanded sea ice can help maintain colder air temperatures and alter storm tracks. Once the North Atlantic enters a colder, icier state, it may resist a quick return to warmth. This helps explain why a triggering disturbance lasting years or decades could lead to a climate reversal lasting more than 1,000 years. The first push does not have to last as long as the consequence. Climate models have explored versions of this problem by adding fresh water to the North Atlantic or Arctic connected regions and watching how the simulated ocean responds. Some experiments show a sharp weakening of overturning circulation and strong cooling in the northern hemisphere. Others depend sensitively on the location, amount, and rate of freshwater input, as well as the background climate state. This variability is important. Models are not time machines that simply replay the past. They are tools for testing mechanisms. They can show that a process is physically plausible, and they can reveal feedbacks that would be hard to see otherwise, but they must be compared with geological evidence. The best explanation is not the one that looks impressive in a model alone. but the one that fits ice cores, marine sediments, lake records, glacial geology, and timing as tightly as possible. Marine sediments add their own clues: tiny shells from foraminifera, chemical ratios, sediment grain sizes, ice-rafted debris, and changes in deepwater indicators can reveal past ocean conditions. If deepwater formation weakens, if currents shift, if sea ice expands, if icebergs carry debris into the ocean, the seafloor can record parts of that story. But marine archives have their own complications. Sediments may accumulate slowly. Ocean mixing can blur signals. Dating marine samples requires corrections because carbon in the ocean does not behave exactly like carbon in the atmosphere. Different basins record different parts of circulation. No single core can speak for the whole Atlantic. Still, when marine evidence is placed beside Greenland ice and terrestrial records, a picture emerges of a northern ocean that changed profoundly during the Younger Dryas. This ocean-centered explanation also helps make sense of geography. The Younger Dryas is especially strong around the North Atlantic region, including Greenland and parts of Europe. That is exactly where a weakening of heat transport would be expected to matter most. The southern hemisphere and tropics do not simply mirror the same cold in the same way. Some regions show different timing, muted responses, or even opposite tendencies, reflecting the seesaw nature of ocean atmosphere connections between hemispheres. This uneven pattern is difficult to reconcile with a simple global dust veil from one cosmic catastrophe, though it does not by itself disprove every possible external forcing. It does, however, strengthen the idea that ocean circulation is central to the event structure. The ocean does not provide every answer. It does not explain every reported microspherule, every black mat, every extinction pattern, or every local ecological shift. It does not remove the possibility that volcanism added an important forcing near the onset. It does not settle the timing of every meltwater route. No single explanation fully accounts for the whole Younger Dryas puzzle. But the ocean offers something crucial, a mechanism capable of turning regional disturbance into long-lasting climate change. It connects melting ice to atmospheric cold, fresh water to sea ice, North American lakes to European forests, and a hidden change in density to a visible change in the living world. So the story passes from ice sheet to lake, from lake to river, from river to sea, and from sea into the deep circulation of the planet. The cold that people felt on land may have begun, or at least persisted, because the ocean stopped carrying heat in quite the same way. Somewhere in the northern waters, the surface may have grown too fresh, too light, too stable. Sinking slowed, warmth stayed farther south. Ice spread its pale skin over dark water. Winds adjusted to the new order, and the world that had been moving toward warmth found itself held, for more than a millennium, in the long cold pause of the Younger Dryas. For the people living near the edge of the Younger Dryas, the climate reversal is not an abstract line in an ice core. It is a change in the ground under their feet, the animals they follow, the plants they know, the rivers they cross, the stones they choose, and the seasons they trust. No one watches the Atlantic circulation weaken. No one measures platinum in snow. No one names the cold interval after a flower. But people feel the consequences of a world becoming less predictable. A hunting route that worked for generations may become less reliable. A wetland may expand, drawing animals into one basin while another dries or freezes longer into the year. A familiar herd may shift its range. A river crossing may become dangerous, then vanish, then return in another place. The Younger Dryas is written in scientific records, but before it becomes science, it is lived as uncertainty. North America during this time contains human communities whose story is more complex than older textbooks allowed. For much of the 20th century, Clovis was often treated as the earliest clear archaeological culture in the Americas, known for its distinctive fluted projectile points, finely made from stone and often associated with large animals. The points are beautiful in a severe way, shaped with skill, symmetry, and technical confidence. The flute, a channel flake removed from the base, may have helped half the point to a shaft or foreshaft, though the exact functional details are still debated. Clovis technology spreads widely across North America within a relatively brief span, and that wide distribution once made it seem like a simple beginning. But archaeology has complicated that picture. Evidence from several sites now indicates that people were in the Americas before Clovis, and probably moved through different landscapes by different routes. Clovis is not the first human footstep. It is one brilliant and visible tradition in a deeper story. That matters because the Younger Dryas has sometimes been folded into a dramatic tale of Clovis people and catastrophe, as if a single climate shock or cosmic event ended a single culture overnight. The archaeological evidence does not support such a clean scene. Clovis technology does fade or transform around the broader Younger Dryas boundary, but human life does not vanish from the continent. People continue living, moving, adapting, making tools, hunting, gathering, and learning altered landscapes. Some traditions change, some technologies become more regional. The broad striking uniformity associated with Clovis gives way to a more varied archaeological pattern. This could reflect population movement, changing prey, social networks becoming more localized, new environmental pressures, or simply the normal evolution of technology in a changing world. Scholars still debate the causes, but the record does not show an empty continent after a single disaster. The people themselves would not have experienced Clovis as a label. They lived in families, bands, alliances, seasonal networks, and remembered places. Their world was made of practical knowledge. They understood stone sources and how different rocks fractured. They knew where animals crossed valleys, where water remained in dry months, where wood could be found, where shelter was possible, and which routes were worth the effort. Many tools were likely made from materials that rarely survive. Wooden shafts, hide bindings, fiber cords, baskets, clothing, bedding, containers, and plant-based equipment. Stone points endure because stone is patient. The rest of life, which may have mattered just as much, often disappears. What survives in the record suggests intelligence and flexibility, but the surviving record is only the skeleton of a much fuller human world. The Younger Dryas would have tested that flexibility. In some regions, colder conditions may have shortened growing seasons and changed the availability of edible plants. In others, shifting moisture patterns may have altered wetlands, grasslands, forests, and animal migration routes. Large animals under ecological stress may have become less predictable, less numerous, or more regionally concentrated. Smaller animals, fish, birds, seeds, roots, and gathered foods likely mattered in ways that are underrepresented archaeologically. A mammoth kill site is spectacular and survives well. A season of gathering plants, repairing clothing, catching fish, carrying water, and maintaining social ties leaves a lighter trace. The dramatic evidence can distort the true balance of daily life. There is also a tendency to imagine Ice Age people as constantly on the edge of desperation. Some communities certainly faced hardship, and climate instability could be severe, but survival was not merely endurance, It was knowledge, it was planning, it was mobility, it was the ability to hold large mental maps of changing terrain. It was the capacity to teach skills across generations, to remember where resources had been found before, to experiment when old patterns failed. People at the Younger Dryas boundary were not passive victims of climate. They are active observers of it, responding at a human scale to changes that scientists now reconstruct at planetary scale. In parts of the American West and Southwest, ancient wetlands, springs, and lake margins may have become especially important. These places attracted animals and preserved archaeological traces, making them appear unusually central in the record. But preservation can create its own illusion. People also lived in uplands, forests, plains, coastlines, and river corridors where evidence may be scarce, eroded, buried, or drowned. The coast is particularly important. Lower Ice Age sea levels exposed vast coastal plains and routes that are now underwater. If early people moved along shorelines, used boats, gathered marine resources, or lived near estuaries, many of their sites may lie beneath modern seas. This missing coastline leaves a quiet gap in the human story just when that story matters most. The Younger Dryas also overlaps with one of the great debates in archaeology and paleontology, how human hunting relates to the extinction of megafauna. People certainly hunted some large animals. Cut marks, tools, kill sites, and butchery evidence show interaction. But the old idea that humans simply swept across the continent and rapidly exterminated every large species by overhunting is too blunt for the complexity of the evidence. Climate change altered habitats. Vegetation shifted. Water sources changed. Reproductive rates differed between species. Some animals may have been more vulnerable because they were already stressed. Human hunting may have been decisive for certain populations in certain regions, especially when combined with environmental pressure. No single explanation fully accounts for all extinctions across all species and places. The human role is real, but it is entangled with a changing world. For the people themselves, the disappearance or decline of large animals would have changed more than food supply. It would have changed movement, tool use, memory, and perhaps the meanings attached to places. A valley where mammoths had once passed might become quiet. A seasonal gathering place might lose its old purpose. Materials from large animals, including bone, hide, sinew, ivory, and fat, may become less available in some regions. New prey and plant resources require new habits. Social networks may stretch or contract as groups adjust to changing opportunities. Archaeology can see some of this only indirectly, through tool forms, site locations, and animal remains. The emotional and cultural dimensions are mostly beyond recovery, though they must have existed. What makes the Younger Dryas human story so compelling is that it sits between visibility and loss. We can see enough to know that people were present, skilled, mobile, and adaptive. We can see that their technologies changed around a time of environmental upheaval. We can see that some of the animals they knew disappeared from the mainland world, but we cannot follow one community through the full cold reversal. We cannot hear their names for the seasons or their explanations for strange weather. We cannot know how they remembered the warming before the cold returned. The evidence remains incomplete, and its incompleteness should make the people more real, not less. They were not symbols in a climate graph. They were human beings living through a world whose causes were hidden from them, even as its consequences shaped every path ahead. The animals of the late Ice Age do not vanish all at once, and they do not vanish only because the air turns cold. Their disappearance is slower, stranger, and harder to compress into a single cause. Still, near the Younger Dryas boundary, North America and parts of the wider world stand close to the end of one of Earth's great mammal ages. Mammoths still move across open country, mastodons still browse in wet woodlands, horses, camels, giant ground sloths, short-faced bears, saber-toothed cats, American lions, dire wolves, and other large animals still belong to the landscape in one region or another. Then, across the transition from the late Pleistocene into the early Holocene, many of them disappear from the mainland record. The timing is not neat enough for a simple verdict, but it is close enough to make the period feel like twilight. A mammoth on the late Ice Age plains is not merely a larger version of an elephant placed in a colder world. It is part of an ecosystem now gone. Its body is built for grinding tough vegetation. Its migrations connect water, grass, snow, minerals, and memory across wide ranges. Mammoth herds shape the land as they move, trample, graze, fertilize, and open paths through vegetation. Mastodons, by contrast, often occupy more wooded or wet environments, feeding on branches, leaves, and aquatic plants. Their teeth reveal a different life. The difference matters because extinction does not fall equally on all animals at once. A change that harms open grassland grazers may not harm wetland browsers in the same way. A change in forest composition may affect mastodons differently from mammoths. The megafauna were not one category of big animals. They were many species with different diets, habits, ranges, and vulnerabilities. The climate reversal arrives at a bad moment for many of them. Before the Younger Dryas, warming had already begun to transform habitats. Forests expanded into some regions, open steppe and grassland systems shifted, wetlands changed, and seasonal patterns altered. Then cooling interrupted or rearranged these trends, for species adapted to large, stable ranges. This kind of oscillation can be more dangerous than steady change. A gradual warming might allow populations to track suitable habitat northward or into new regions. A sudden cooling after a warming pulse can fragment those habitats, trap populations between changing plant communities, and reduce the predictability of food. Large mammals often reproduce slowly. They cannot recover quickly from repeated poor years, reduced forage, disease stress, or increased hunting pressure. Their size gives them power, but it also makes them vulnerable to long ecological disruption. Human pressure adds another layer, and it cannot be ignored. People hunted large animals in the late Pleistocene. The evidence is not imaginary. There are kill and butchery sites, embedded points, cut marks, broken bones, and tool associations that show direct interaction with mammoths, mastodons, and other animals in some places. A human group does not need to kill every animal to matter. If a species reproduces slowly and is already stressed by climate and habitat change, even modest additional mortality can push local populations downward. Hunting may have been especially significant near water sources, migration bottlenecks, or seasonal gathering places, yet the evidence does not support a simple picture of people exterminating all megafauna everywhere in one rapid wave. Some species decline before the strongest Younger Dryas signal. Some persist longer. Some regions show different patterns. Scholars still debate the relative weight of hunting, climate, ecological cascade, and disease, but most serious explanations now involve more than one pressure. This is where the Younger Dryas becomes both relevant and insufficient. The cold reversal may have worsened stress at a critical time. It may have changed vegetation, water, snow cover, migration routes, and reproductive success. It may have reduced the resilience of species already facing human predation and habitat fragmentation, but it does not neatly explain why some animals vanish while others survive. Bison survive and eventually thrive in altered forms. Deer, elk, pronghorn, bears. Wolves and many smaller mammals continue. Some large animals disappear in North America but had vanished earlier or later elsewhere. The pattern is selective, a cosmic blast, a cold snap, or a hunting wave alone struggles to explain that selectivity. No single explanation fully accounts for this extinction pattern, because the animals were embedded in food webs, landscapes, and histories that differed from place to place. One lesser-known detail is that some extinctions have long tails. Woolly mammoths disappear from most mainland regions by the end of the Pleistocene, but isolated populations survive much longer on islands. On Wrangel Island in the Arctic Ocean, mammoths persist into the Middle Holocene, thousands of years after the Younger Dryas ends. This does not mean the mainland extinction was unimportant or slow everywhere, but it complicates the image of one terminal catastrophe: isolation. Reduced predators, different human access, and local ecology allowed some animals to linger in refuges after their continental world had collapsed. Extinction, seen up close, is often less like a door slamming and more like lights going out in different rooms at different times. The disappearance of megafauna also changes ecosystems in ways that ripple beyond the animals themselves. Large herbivores are engineers. They break branches, spread seeds, maintain open habitats, disturb soil, recycle nutrients, and influence fire regimes. When they vanish, vegetation can change not only because climate changes, but because the animals that once shaped plant communities are gone. Shrubs may thicken, forests may close in certain areas, grasslands may lose some of their grazing pressure, predators lose prey, scavengers lose carcasses, humans lose sources of meat, fat, hide, bone, and ivory. The end of the Pleistocene is therefore not only a list of vanished species, it is an ecological reorganization, a rewriting of relationships. Fire may also shift in this new animal world. In some ecosystems, large grazers reduce fuel by consuming grasses and trampling vegetation. Remove them, and plant material may accumulate differently. But climate controls moisture, wind, and lightning. Humans can ignite fires. Vegetation type determines fuel structure, and wetlands or drylands respond in opposite ways. Charcoal records near the Younger Dryas boundary are therefore hard to interpret. Increased burning in one region may reflect drought, vegetation change, human activity, loss of grazing pressure, or several factors combined. The evidence remains incomplete, and the temptation to make fire a single dramatic cause should be resisted. Fire is often a messenger of change rather than the author of it. For human communities, the fading of megafauna would have been gradual enough in some places to be experienced as change, not apocalypse, but fast enough in ecological terms to matter deeply. A generation may notice that certain animals are harder to find. Another may travel farther for the same returns. Toolkits adapt. Hunting strategies shift towards smaller game, fish, birds, and more regionally available resources. Plant foods, always important, may become more visible in daily survival, even if they leave fewer archaeological traces. Social territories may change as people follow new seasonal patterns. The end of the mammoth world does not end human life. It pushes human life into new forms. The most dramatic animals tend to dominate the imagination, but their absence is also a clue to the future. The Holocene world that follows the Younger Dryas is not empty, but it is missing a category of presence that had shaped continents for millions of years. When the climate warms rapidly after the cold interval, it does so into a world without many of the giants that once moved through it. Forests, grasslands, wetlands, and human societies develop under that new condition. The landscape modern humans inherit is already a post-extinction landscape. Its normality is built on loss. So the megafauna stand at the edge of the Younger Dryas as witnesses rather than simple victims of one cause. Their bones record diets, movement, stress, hunting, and disappearance, but not one universal explanation. Their decline overlaps with abrupt climate change, human expansion, habitat disruption, and ecological feedbacks. The puzzle is not whether the world changed around them. It did. The puzzle is how many pressures were needed to push so many species beyond recovery, and why some endured while others vanished. In the long cold pause of the Younger Dryas, the giants of the Pleistocene are already becoming memories written in bone. After the giants begin to fade from the record, the landscape itself seems to change its voice. The clues become quieter, but not less important. Charcoal appears in some sediments. Dust increases in some archives. Wetlands expand in some basins and retreat in others. Forests hesitate, thin, or reorganize. Open ground spreads in places where warmer conditions had allowed shrubs and trees to gain a foothold. The Younger Dryas is often imagined through a single dramatic picture, a burning sky or a collapsing ocean current, but much of its evidence is more subtle than that. It is found in the way soil moves, in the way plants fail to return, in the way wind carries exposed ground into lakes and ice, in the way silence gathers where an ecosystem has lost some of its largest bodies. Fire is the most visually powerful of these clues, and therefore one of the easiest to overstate. A layer of charcoal seems to promise a story. Something burned. Something must have happened. But fire is one of Earth's oldest habits. Lightning ignites dry vegetation. Humans use fire for warmth, cooking, protection, landscape management, tool preparation, and daily life. Drought can turn ordinary sparks into large burns. Shifts in vegetation can create new fuel patterns. The loss of large grazing animals can allow plant material to accumulate differently. A cooling climate can still produce dry seasons. A warming interval can still leave enough fuel for later fires. So when charcoal appears near the Younger Dryas boundary, it does not speak with one meaning. It asks to be placed in a local landscape, beneath a local sky, among local plants, winds, animals, and people. This is why the idea of continent-wide fires at the Younger Dryas onset remains disputed. Some records show increased burning, others do not. Some charcoal peaks may be real signals of unusual fire activity, others may reflect local conditions, redeposition, or changes in sediment preservation. A marsh can concentrate charcoal washed in from nearby slopes. A lake can receive burned fragments from a catchment larger than the visible basin. A dry interval can increase fire. But a wetland can preserve the evidence better than a dry upland. The evidence remains incomplete, and its incompleteness matters. If a cosmic airburst had ignited vast fires across a continent, scientists would expect a more consistent and diagnostic pattern than the record has so far provided. The fire clues are real in places, but they do not all align into one clean burn scar. Dust tells a different story, colder and more patient. In ice cores, lake beds, loess deposits, and marine sediments, dust can signal exposed ground, stronger winds, reduced vegetation cover, and drier conditions. At the end of the Ice Age, vast areas near retreating glaciers are vulnerable to wind. Newly uncovered sediments have not yet been stabilized by mature soils and plant roots. Braided rivers carry glacial flour, then leave fine material exposed across floodplains. Seasonal drying can turn these surfaces into sources of airborne particles. A colder Younger Dryas climate can reduce vegetation growth in some regions, allowing wind to take more from the land. Dust is not a spectacular clue, but it is one of the clearest signs that the surface of the Earth itself was unsettled. In Greenland ice, increased dust during colder intervals suggests a world with stronger atmospheric circulation and broader exposed landscapes. The dust does not need to come from one nearby source. Fine particles can cross long distances, carried by winds from dry continental interiors. Each grain is small, but together they mark a change in the planet's skin. Less plant cover, more exposed sediment, colder air, altered storm tracks, and shifting moisture all contribute to a dustier world. This is one of the quieter consequences of abrupt climate change. The land becomes more available to the wind. Drought and wetness both appear in the Younger Dryas story, depending on where one looks. This can seem contradictory until the geography is taken seriously. A cold reversal does not mean every place simply becomes colder and drier in the same way. Atmospheric circulation shifts can bring drought to one region and increased moisture to another. Lower evaporation in cold conditions can preserve wetness in some basins, while reduced precipitation can dry uplands elsewhere. Springs may strengthen where groundwater systems respond to changing recharge or pressure, while lakes elsewhere shrink. The black mats discussed earlier belong partly to this complexity. Their dark sediments can record wetter local conditions even while the broader regional climate is stressed or seasonally severe. No single explanation fully accounts for every wetland, every dust layer, and every charcoal peak, because the Younger Dryas is not one uniform climate blanket laid over the world. Vegetation records show the ecological consequences of these uneven changes. In parts of Europe, plants associated with colder, more open environments return. In North America, plant communities reorganize in ways that differ by region. Spruce, pine, grassland, tundra-like vegetation, wetland plants, and parkland environments move in patterns controlled by temperature, moisture, soil, fire, and animal pressure. A forest does not simply march north or south like an army. Trees spread through seeds, and seeds depend on wind, animals, soil, moisture, and time. A sudden cold reversal can interrupt expansion before mature forests establish. It can strand patches of vegetation in places where the climate no longer favors them. It can create mosaics of old and new communities living side by side for a time, like overlapping maps that no longer perfectly match. The disappearance of large herbivores may have deepened these changes. Mammoths, mastodons, horses, camels, and giant ground sloths were not just animals moving through scenery. They were part of the machinery that maintained scenery. Their feeding, trampling, dung, path-making, and seed dispersal influenced the structure of plant communities. As their numbers fell, landscapes may have become brushier or more wooded in some areas, or changed fuel patterns in ways that affected fire. But this cannot be treated as a universal rule. Climate, soil, and moisture still set strong limits. In some regions, cold and dryness may have prevented dense vegetation regardless of animal presence. In others, the loss of grazers may have mattered greatly. Scholars still debate how far megafaunal decline reshaped vegetation, but the possibility adds another feedback to an already crowded system. There is a haunting kind of silence in this part of the record, not silence because nothing happens, but silence because many of the most important changes leave no dramatic artifact. A species becomes rarer before it disappears. A migration route fails for several seasons. A plant community loses resilience. A wetland shifts chemistry. A spring changes flow. A human group returns to a place and finds fewer animals than expected. These things do not always create a clear layer. They may leave only a change in pollen percentages, a gap in bones, a different stone tool distribution, or a charcoal curve that rises and falls without explaining itself. The Younger Dryas is not only a catastrophe to be detected, it is a long interval of altered expectations. Volcanic forcing adds still another shadow to the scene. Large eruptions can inject sulfate aerosols into the atmosphere, reflecting sunlight and cooling the surface for years. They can alter precipitation patterns and stress climate systems already near thresholds. Newer geochemical work suggests that some signals once interpreted as possible cosmic evidence may fit volcanic sources more convincingly. If volcanic activity occurred near the critical window, it may not have needed to act alone. It could have nudged a vulnerable North Atlantic system, strengthened sea ice feedbacks, or combined with meltwater freshening to help push the climate into a colder mode. What survives in the record suggests a world where several forces may have overlapped, each one insufficient alone, but dangerous together. So fire, dust, drought, wetland growth, vegetation change, megafaunal decline, human adaptation, volcanic chemistry, and ocean circulation all gather around the Younger Dryas boundary. None is silent, but none speaks the whole truth by itself. Fire shows disturbance but not always cause. Dust shows exposure but not always trigger. Wetlands show hydrological change but not universal climate. Charcoal shows burning but not necessarily catastrophe. The absence of animals shows loss but not one simple killer. The landscape becomes a chorus of partial evidence, and the task is not to force every voice into the same note. It is to hear the pattern without pretending the pattern is simpler than it is. By the time all the clues are gathered, the Younger Dryas no longer looks like a mystery with too little evidence. It looks like a mystery with too many possible entrances. One path begins in the sky, with the disputed idea of a comet or asteroid fragment exploding above the late Ice Age world. Another begins in the ice, with meltwater from North America diluting the northern seas and weakening Atlantic circulation. Another begins beneath the crust, with volcanic eruptions sending aerosols and unusual metals into the atmosphere at a moment when climate was already unstable. Another begins in the living world, with humans hunting large animals, habitats shifting, fires changing, and ecosystems losing resilience. Each explanation catches part of the light. None, by itself, cleanly illuminates the whole room. The cosmic impact hypothesis has the strongest dramatic pull because it offers a single violent moment. It seems to explain why the Younger Dryas feels abrupt, why strange particles have been reported at some sites, why rare metal anomalies attracted attention, why fires became part of the story, and why the extinction of megafauna appears near the same troubled boundary. But its weakness is also its simplicity. The evidence for a confirmed impact remains disputed. No universally accepted crater has settled the case. Some proposed markers can be made by terrestrial processes. Some claims have been difficult to reproduce. Some signals are not precisely timed to the onset. Recent withdrawals and corrections around impact-related papers have made the strongest versions of the claim harder to sustain. A cosmic event remains an idea that can be discussed, but not a foundation on which the entire Younger Dryas story can safely rest. The freshwater and Amo Sea explanation is quieter but more physically rooted. It does not require a flash in the sky. It begins with a known reality. Huge ice sheets were melting, vast lakes were forming, and the North Atlantic circulation is sensitive to salinity and density. Fresh water entering the wrong place at the wrong time could reduce deep water formation, weaken northward heat transport, expand sea ice, and plunge the North Atlantic region back into cold. This explanation fits the geography of the cooling better than many alternatives. The Younger Dryas is especially powerful around the North Atlantic world, where changes in ocean circulation should matter most. Yet this model has its own unresolved problems. Scholars still debate the timing, route, and volume of meltwater discharge. Some proposed drainage pathways are difficult to prove. Some records fit better than others. The mechanism is plausible and widely taken seriously. But the ancient plumbing of deglaciating North America is still not mapped with the precision one would want. The volcanic explanation has gained new force because it speaks directly to some of the geochemical clues that once seemed to point beyond Earth. Large eruptions can inject sulfate aerosols high into the atmosphere, reduce incoming sunlight, cool the surface, alter rainfall patterns, and disturb climate circulation. Volcanic systems can also produce or distribute unusual chemical signatures, including signals involving platinum group elements and related metals. Newer work suggesting that osmium isotopes and highly siderophile elements in North American sediments fit volcanic forcing better than extraterrestrial input is important because it does not deny the strange chemistry. It reassigns its source. The clue remains real, but its meaning changes. Instead of a cosmic fingerprint, it may be a volcanic one. The uncertainty lies in scale, timing, and climate effect. A volcanic episode might cool the planet for years, but the Younger Dryas lasts more than a millennium, so volcanism alone may be too short-lived unless it acts as a trigger, reinforcement, or first push into a longer ocean ice feedback. This is where the explanations begin to overlap rather than compete cleanly. A volcanic pulse could help cool the North Atlantic region just enough to encourage sea ice growth. Expanded sea ice could alter ocean-atmosphere exchange. Meltwater freshening could weaken circulation further. A weakened AMOC could reduce heat transport and keep high northern latitudes cold. Dust, vegetation change, and snow cover could modify the surface response. In such a model, the most important cause is not one actor, but sequence. A stressed climate system may not need a giant blow. It may need a series of smaller pressures arranged in the wrong order. No single explanation fully accounts for this, but a cascade model has the advantage of matching the messy character of the evidence. Human hunting and ecological collapse belong to the same problem at a different scale. They cannot explain the abrupt cooling recorded in Greenland ice. People with stone tools did not weaken the Atlantic circulation or inject volcanic aerosols into the stratosphere. But humans may have mattered greatly for the fate of large animals and for local ecosystems already under climate stress. Hunting pressure on slow-reproducing megafauna can become decisive when populations are fragmented by habitat change. Fire use can alter local vegetation. Movement into new regions can reshape predator-prey relationships. The role of humans is therefore not as the cause of the Younger Dryas climate event, but as part of the biological transformation occurring through it. The extinction story and the climate story overlap, but they are not identical. Ecological collapse is also not a single mechanism. It is a pattern that can emerge when many relationships weaken at once, change the plants, and herbivores struggle, remove large herbivores, and plants change again, shift water sources, and animals concentrate in fewer places, increase fire in some regions, and vegetation reorganizes, add human hunting, and stressed populations may fail to recover, cool the climate abruptly, and migration routes or breeding seasons may no longer align with food availability. The evidence remains incomplete because ecosystems do not leave tidy cause and effect diagrams in the soil. They leave pollen, bones, charcoal, dung fungi, isotopes, and absences. Sometimes the absence is the most important clue. The strongest current interpretation is therefore not the most spectacular one, but the most layered. The Younger Dryas cold reversal seems best understood as a climate system event centered on ice, ocean, atmosphere, and feedbacks, possibly influenced or intensified by volcanic forcing, with ecological and human consequences unfolding unevenly across landscapes. The cosmic impact hypothesis remains part of the history of the debate and part of the popular fascination, but it should not be presented as established fact. Its evidence has been too contested, its markers too ambiguous, and some of its supporting claims too weakened by later scrutiny. The more durable mystery is not whether one comet changed everything. It is how close the late Ice Age Earth already was to a threshold, and how many different pressures had to converge before the system crossed it. That answer is less simple, but it is more unsettling in its own way. A single cosmic disaster is terrifying because it is sudden. A cascade is terrifying because it means a world can be fragile before anyone notices. Ice can melt for centuries. Lakes can swell behind frozen dams. Oceans can grow fresher. Sea ice can expand. Volcanoes can darken the sky for a few seasons. Animals can lose resilience, and then a familiar climate can slip into another mode. The Younger Dryas may not be the story of one hammer blow, it may be the story of a planet already full of cracks. The Younger Dryas endures because every answer seems to solve one part of the mystery, while leaving another part restless. The cold reversal itself is no longer in serious doubt. Greenland ice, European pollen, marine sediments, lake records, glacial evidence, and ecological shifts all point toward a real and abrupt reorganization of climate near the end of the Ice Age. The debate is not whether the event happened. The debate is how to connect the pieces without forcing them into a story cleaner than the evidence allows. A single cause would be satisfying, a single trigger would be easy to remember. But Earth rarely gives its deepest histories in simple shapes. One reason the puzzle remains difficult is that the Younger Dryas sits at the intersection of many archives, and each archive speaks a different dialect. Ice cores offer timing and atmospheric chemistry with remarkable precision, but they do not directly show what happened in every lake, river, forest, or human camp. Lake sediments can preserve local ecology beautifully, but they may be disturbed by shoreline change, erosion, floods, or shifts in water chemistry. Marine sediments can reveal ocean circulation, sea ice, and deep water changes, but dating them can be complicated by reservoir effects and slow accumulation. Caves can protect bones and minerals, but they record only the narrow world that enters the cave. Archaeological sites preserve human traces, but only a tiny fraction of human life survives as stone, bone, and charcoal. Each record is truthful in its own limited way. The difficulty lies in making them speak to one another. Timing is the most stubborn problem of all. The Younger Dryas onset is often described around 12,900 years ago, but a date written in a summary is far sharper than a date recovered from sediment. Radiocarbon ages have error ranges. Calibration curves introduce complexity. Different materials can give slightly different ages. A charcoal fragment may not date the moment of burning if the wood was old when it burned. A bone may move from one layer into another. Groundwater can bring old carbon into a wetland. Marine organisms can appear older because of carbon dissolved in the ocean. Even ice core chronologies, among the best available, require synchronization and interpretation. In a mystery where a clue arriving 50 years before or after the onset can change its meaning completely, chronological uncertainty is not a minor nuisance. It is the hinge on which whole theories swing. This is why the recent rethinking of platinum matters so much. A platinum spike can sound dramatic, especially when people associate platinum group elements with extraterrestrial material. But if the spike appears after the Younger Dryas cooling has already begun, and if a volcanic origin is plausible, then it cannot bear the weight that some versions of the cosmic story placed on it. The clue does not vanish. It becomes more interesting in a different way. It may record volcanic disturbance, atmospheric transport, or another episode in a climate already reorganized. But it is no longer safe to treat it as the match that lit the whole event. In the Younger Dryas puzzle, chronology repeatedly turns apparent answers into more complicated questions. Reproducibility is another reason the debate continues. A reported microspheral peak, nanodiamond layer, shocked quartz signal, or melt glass concentration must be found again, identified again, and interpreted consistently by other researchers. This is not because science is hostile to bold ideas. It is because nature is full of things that imitate one another. Volcanic particles can resemble impact products. Biological remains can be mistaken for exotic grains. Ordinary geological processes can concentrate unusual materials in thin layers. Fire can alter minerals. Water can sort particles by density. Wind can carry distant dust. If one laboratory sees a dramatic signal and another cannot confirm it, the question does not end immediately, but the claim becomes weaker. The burden shifts back to methods, sampling, definitions, and context. The Younger Dryas impact hypothesis has suffered especially from this burden. Some of its proposed evidence has been challenged on grounds of identification, dating, or geological plausibility. Some high-profile claims have later been withdrawn or heavily criticized. For a general audience, retractions may sound like scandal, but they are also part of the self-correcting machinery of science. A paper enters the record, other experts examine it, problems emerge, and the record is revised. This process can be uncomfortable, especially when an idea has already become famous outside specialist circles. But discomfort is not the enemy of knowledge. It is often the price of better knowledge. At the same time, the persistence of debate should not be mistaken for equality among all explanations. Not every hypothesis stands on the same ground. Freshwater forcing and AMO sea weakening are supported by known physical mechanisms and by the geography of the cooling, though details remain debated. Volcanic forcing has gained strength as a way to explain some geochemical signals and perhaps provide an initial climatic nudge, though it also must be tested against timing and scale. Human hunting and ecological stress help explain parts of the megafaunal story, but do not explain the abrupt climate reversal itself. The cosmic impact hypothesis remains controversial and, in its strongest form, poorly accepted by many specialists because too many of its key claims remain disputed. A balanced script does not give every idea the same weight. It gives each idea the weight its evidence can carry. Another reason the Younger Dryas endures is that different fields ask different questions. A climate scientist may focus on ocean circulation, sea ice, and temperature records. A geochemist may focus on osmium isotopes, platinum group elements, and volcanic aerosols. An archaeologist may focus on human settlement, tool traditions, and site formation. A paleontologist may focus on extinction timing and population vulnerability. A paleoecologist may focus on pollen, dung fungi, charcoal, and vegetation change. Each field has its own methods and standards of proof. When their evidence overlaps, the result can be powerful. When it conflicts, the conflict may reflect real complexity rather than error. The Younger Dryas sits in precisely that uncomfortable place, where many specialists are each partly right, but no discipline alone can finish the story. There is also the problem of missing evidence. Much of the late Ice Age coastline is underwater. Many river valleys have been reworked, ice sheets destroyed or buried older landscapes, organic materials decayed, human camps made of hide, wood, fibre, and memory vanished almost entirely. Animal populations could decline across wide regions without leaving continuous records. Volcanic aerosols could spread thinly and unevenly. Meltwater routes could open, close, and leave only partial traces. The absence of evidence can mean something did not happen, or it can mean the record failed to preserve it. Distinguishing between those possibilities is one of the hardest tasks in deep-time science. And still, the Younger Dryas remains irresistible because it feels close. 12 or 13,000 years is ancient in human history, but young in Earth history. People were here. The animals were familiar enough to imagine and strange enough to feel lost. The climate system that shifted then is not an alien machine. It is an earlier version of the same planet humans inhabit now. The event shows that climate can change abruptly when ice, ocean, atmosphere, and feedbacks align. It shows that ecosystems can cross thresholds. It shows that evidence can be real and still misunderstood. It shows that a mystery can become deeper not because science fails, but because science learns to stop accepting the easier story. So the puzzle endures not as a failure of explanation, but as a warning against premature certainty. The Younger Dryas is not a blank space. It is crowded with clues, ice core signals, pollen shifts, meltwater routes, volcanic fingerprints, rare metals, disputed particles, black mats, animal disappearances, human adaptations, sea ice feedbacks, and ocean circulation changes. The challenge is not to find one clue and declare the case closed. The challenge is to understand how a world at the edge of the Ice Age became vulnerable enough that several clues could belong to the same unfolding crisis. The mystery survives because the truth is likely not a single event, but a chain of events, and chains are always harder to see once most of their links have been buried. The Younger Dryas does not end quietly, at least not in the climate record. After more than 1,000 years of cold, the world warms with a speed that seems almost as startling as the cold reversal itself. Around 11,700 years ago, the long pause breaks. Greenland ice records a rapid shift toward milder conditions. Dust decreases, temperature signals rise, atmospheric patterns reorganize. In many regions around the North Atlantic, the severe edge of the late glacial world begins to soften again. The Younger Dryas, which had felt in the records like a return to an older Ice Age rhythm, gives way to the Holocene, the warm interval in which agriculture, villages, cities, writing, kingdoms, empires, and modern civilization will eventually appear. But at the moment of transition, there are no cities yet. There are only people, animals, rivers, forests, coasts, and ice learning new shapes. The end of the Younger Dryas is one of the great reminders that climate can change in both directions abruptly. The same system that can slip into cold can also climb out of it quickly when ocean circulation strengthens. Sea ice retreats, greenhouse gases, winds, and feedbacks align, and the surface of the planet begins absorbing and moving heat differently. The exact sequence remains debated, But the broad transformation is clear. The northern hemisphere warms. The North Atlantic world changes. Forests expand again into regions where cold, open vegetation had returned. Lakes alter their chemistry and levels. Glaciers retreat. Sea level continues its long rise as ice melts. The cold flower that gave the Younger Dryas its name loses ground as warmer plant communities push back into the landscape. For humans, the end of the Younger Dryas opens possibilities that would have been difficult during the cold reversal. The early Holocene does not become paradise. Weather remains variable. Sea level rise floods coastal plains. Animal communities are changed forever. Many of the great Pleistocene mammals are gone from mainland landscapes. Yet the climate becomes more stable in ways that matter deeply. Seasonal patterns become easier to rely on in many regions. Forests, wetlands, grasslands, and river systems settle into new arrangements. People continue adapting, not as survivors of one event alone, but as inheritors of a transformed Earth. In the centuries and millennia that follow, some communities in different parts of the world begin experimenting more intensively with plants, animals, settlement, storage, and landscape management. The Holocene does not cause civilization in a simple way, but it creates a climatic backdrop in which new human worlds can take root. The oceans continue rising, and this is one of the quieter tragedies of the transition. Lands that had been home to animals and people vanish beneath shallow seas. Coastal routes, camps, estuaries, shellfish grounds, river mouths, and plains are drowned. Some of the most important records of late Ice Age and early Holocene life may now lie underwater, broken by waves or buried under marine sediment. The world that people knew at the end of the Younger Dryas is not merely changed by climate. It is physically removed from the map. Modern shorelines are not the ancient shorelines. The sea has covered many of the paths by which humans moved through the changing world. The evidence remains incomplete partly because the planet itself has hidden the evidence. The legacy of the Younger Dryas is therefore not only scientific, it is geographical, ecological, and human. The event stands near the boundary between the Pleistocene and the Holocene, between the age of mammoths and the age of farming, between a world of vast ice sheets and a world of rising seas. It is not the only reason those changes happened, but it belongs to the threshold. It shows how strongly Earth's systems are connected. Ice on one continent can influence the saltiness of an ocean. Ocean circulation can influence air temperature across another continent. Volcanic chemistry can appear in ice and sediments thousands of kilometers away. A dark wetland layer can become part of a debate about climate, extinction, and cosmic catastrophe. A rare metal spike can look like a message from space, then become a fingerprint of Earth's own volcanism. The Younger Dryas teaches that clues are not always wrong when their first interpretation fails. Sometimes they are pointing to a different story. This is perhaps the most important change in how the mystery should now be told. The older, more dramatic question asked whether a comet changed the Ice Age. The better question is broader and more unsettling. How did an already unstable Earth system become vulnerable enough for abrupt cold to return? And what combination of ice, water, ocean, atmosphere, volcanic forcing, and ecological stress made that reversal endure? The cosmic impact hypothesis remains part of the history of the debate, and it still has supporters, but it cannot be treated as settled fact. Too many key markers are disputed. Too many timelines are uncertain. Some claims once used to strengthen it have weakened under later scrutiny. Meanwhile, volcanic interpretations of geochemical signals and freshwater-driven weakening of Atlantic circulation offer a more grounded path through the evidence. though even that path still has gaps. The Younger Dryas also leaves a lesson about mystery itself. A mystery does not become less powerful when a simple answer fails. Sometimes it becomes more powerful because the true shape is larger. A comet strike is dramatic for a moment. A climate cascade is dramatic for a millennium. It means the world can change not only from one violent interruption, but from the accumulation of pressures inside systems that appear stable until they are not. It means the past was not a sequence of isolated events, but a web of thresholds, ice sheets, meltwater lakes, sea ice, winds, volcanoes, forests, animals, and people all belong to that web. When the Holocene finally arrives, it does not erase the Younger Dryas. It builds over it. Forest roots grow through older sediments, rivers cut into former shorelines. New animals move through spaces once crossed by vanished giants. Human communities carry forward, adapting to a warmer and increasingly recognizable world, while the cold interval sinks into mud, ice, pollen, and seabed. For thousands of years, no one knows its name. Then drills enter the ice, cores rise from lakes. Microscopes search dark grains, and the old cold returns as evidence. The Younger Dryas becomes visible again, not as a myth of one perfect catastrophe, but as a warning written by a planet that once turned back toward winter, just as spring seemed near. The story ends, if it ends at all, not with a crater, not with a single blackened layer, not with one final verdict, but with a landscape growing warmer beneath a changed sky. The ice retreats farther into the north. Rivers find new beds. Forests spread their shade over ground that had known tundra and wind. Lakes calm, wetlands thicken. The bones of mammoths and mastodons settle deeper into silence. The people who remain do what humans have always done. They move, remember, learn, and remake their lives around the world that is available to them. There is something quietly humbling about the Younger Dryas because it refuses to become simple. It asks us to imagine a planet where causes overlap, where clues mislead without being false, where a strange metal in the ice may belong not to the stars but to a volcano, where a dark layer may speak not of one fire but of water, plants, and time. It asks us to accept that the past is not always a locked room with one hidden key. Sometimes it is a ruined landscape after the weather has passed, and every surviving trace tells only part of what happened. Yet that is also why the mystery lasts. It brings the distant ice age close enough to feel. A cooling ocean, a restless ice sheet, a wind full of dust, a spring-fed marsh darkening with organic matter, a human path along a river, a herd moving through a narrowing world. These are not abstractions. They are the textures of a living planet. For a little more than 1,000 years, Earth held part of the northern hemisphere in a cold pause, then released it again into warmth. From that release came the early Holocene world, and from that world, eventually, came the long human experiment of settlement, memory, and civilization. But beneath that later story lies the older one, still preserved in frozen air and buried pollen. It is the image of a world almost out of the Ice Age, suddenly pulled back toward cold, then lifted again into light, and somewhere in that long transition, between melting ice and rising sea, between vanished animals and the first outlines of the world we know, the Younger Dryas remains not a solved riddle, but a deep mark in time, waiting in the quiet layers of the earth.